This question is from Rotational Motion. Check your understanding, question number 8 from the book Pathfinder. It is a very amazing toppling question. So let us see what is the question and how do we solve it. Question is, such a small block is released on the top of a wedge. So you can see this is the wedge that is placed on a horizontal floor. So this is the horizontal floor. Now mass of the wedge is m and angle of inclination is theta. So this is angle of inclination. Friction between the wedge and the floor is sufficient to prevent sliding. So they're talking about here. So wedge is not sliding. And the coefficient of friction between the wedge and the block is mu. So here coefficient of friction is mu. We have to find out the mass of the block such that wedge will not topple. So in this case, in this question, there are two cases. First case is that if this block slides, this will not slide because it is given here friction is enough. So there are two possible scenarios. One scenario when this will slide and another scenario when this will not slide. So both we will see one by one. So first let us see that when this is not sliding. If this is not sliding, that means mu is greater than tan theta, right? I hope you know this calculation. Mg sin theta is then less than mu mg cos theta. So maximum and then friction is not yet limiting. So that is how you get mu is greater than. If mu is greater than tan theta, so that means friction is enough here to prevent the sliding, right? So block will not slide in this case. Net force on the wedge due to the block will be mg. So this is a crucial point. Now here, this is the block, right? So if you think about the free body diagram of this block, then the only force acting on this is mg downward, right? Which is not the force, or let us draw the free body diagram of this. This is m. On this, force acting is downward, gravity, but it is not moving. So that means now there are two forces which are acting from the wedge on the block. One is what? Normal, another is friction. But resultant of both, if you think carefully, resultant of both have to be mg upward, then only it is not sliding. Fine. So that is what is happening. So here now, that is what I've written here. Net force on the wedge due to the block will also be mg, x and x. Now let us see free body diagram of the wedge. Free body diagram of the wedge. Now here, since block is small, it is written in the question, we can assume that as point mass. So mg is acting on this reaction. So when mg is acting on this, then line of action of mg is passing through this point. Now, if at all wedge will topple, it will topple about this point like this, right? So in this, let us see what happens now. So I've taken this as origin, this as L, and this is H. So normal here will be m plus m mg. M is mass of the wedge, small m is mass of the block. So normal is total mass into G. Now mg will act at L by 3 distance. So coordinate of this, if you write, this will be center of mass is at centroid. So L by 3 and H by 3, this distance is L by 3. So mg into L by 3, I'm writing torque about this point. Now see here, torque of mg, the small mg, will be 0 about this point. Fine. So if torque of small mg is 0, then there are two forces which are providing torque. This mg, so mg into L by 3, and this normal. Normal is m plus mg. So you find x then. What is x? X is the distance of normal or line of action of normal from this face, from this edge, right? So this x is this. Now see here. X tends to 0, it does not become 0. It tends to 0 when m tends to infinity. So when small m, the block, mass of the block becomes very, very large, then this x will tend to this, right? So in that case, we can say that it is never going to topple because x will not become 0. It will tend to 0, right? The block will topple when normal has a tendency to go out of this, right? Somewhere here. Then it will topple. So here, what is the conclusion then? X tends to 0 when m tends to infinity. So if block is not sliding, that means this wedge is never going to topple. That is first case. Let us now, I hope this is clear to you. Let us now go to the second case when the block is sliding. Block is sliding, that means automatically mu is less than tan theta. Friction is not enough to prevent sliding of the block. In that case, this is the free body diagram of the block. Mg sin theta, friction has become limited, mu mg limiting, mu mg cos theta, normal, and mg. So block is moving like this, normal is equal to mg cos theta, right? Now the reaction of this and this will act on the wedge. You know? So mg is acted by the earth center. So reaction of that will act on the earth center. but this normal is applied by the wedge. This friction is also, these are contact forces applied by the wedge. So reaction of this will act here and reaction of this will act here. Now, if you see, the line of action will not pass through this, right? Here friction value is different. So let us see what happens now. I'm still again now writing the talk about this point. Now I am taking the limiting case, extreme case, when it is just about to topple. So when it is just about to topple, the normal has shifted, like in previous simple questions of toppling, normal has shifted here. Now there is no scope for normal to shift. So any mass which is more than the value which we are going to calculate, it will topple like this. About this point, it will topple this way. Fine. So we'll calculate the limiting value, maximum value of M, by writing torque equal to 0 about this point. Fine. So let us see which all forces are going to provide torque. This is mg into L by 3. This is clockwise torque. So you can write like this. This is the point. This is mg. So it will try to rotate this way. So clockwise torque. Now if you see mu mg cos theta is also trying to rotate this way. So mu mg cos theta torque will also be added. Now mu mg cos theta is acting this way. And if you drop a perpendicular here like this, so when we drop a perpendicular, then this is the perpendicular distance, L cos theta, L sin theta. So that is what I have written, L sin theta. Now this torque needs to be balanced by small n, sorry, n, normal reaction. So for n now, this is n cos theta line is passing through this, n sin theta into h we can write. N is mg cos theta. See here, n is mg cos theta. So it is, so here, this is n cos theta, line of action is passing through. And this is n sin theta. So torque of n about this point, you know, is n sin theta into h. N is mg cos theta, sin theta into h, right? Now after that, I'm dividing by L and G will cancel. So when you divide by L and G, it becomes this, m by 3 plus mu m sin theta cos theta, and m now simultaneously h by L I have written here as tan theta. You can calculate and see some of these steps I have skipped, not written. So this becomes m sin square theta. You can see here tan h by L is tan theta. So sin theta by cos theta cancels, becomes sin square theta. And we have to find out the value of small m. So small m sin theta is equal to m by 3. So this is the value of m. Fine. If mu is less than tan theta. So these are two answers, two cases. First case when it is not toppling. Second case, first case when it was not sliding. That time, irrespective of the value of m can be infinite, very, very large also. It will not topple. But now here when mu is less than tan theta, then if this is the minimum value, if m becomes more than this, it will topple then, right? So that's it. It is a very amazing question of toppling, very, very highly probable question. Something based on this can definitely come in JEE Advanced. Thank you very much for watching. If you have studied, if you learned something from this video, please subscribe to this channel and please give a like to this video also. Thanks a lot. All the best. I'll see you in next video.